In this video for the chapter DC circuits, we will be solving some of the more problems, and it will be based on the principles of symmetry which we discussed in the last video. If you have not seen the previous video, I would just suggest you to go back and see the previous video where we introduced the concept of symmetry, of horizontal symmetry and vertical symmetry, because we will be extensively using the rules of those symmetries today in solving a couple of questions. So let us start with our first question. So as you can see that in this problem, the circuit is quite complex. So we can either use KCL and KVL, and we can easily identify 4 non-overlapping loops. But 4 non-overlapping loops means that we need to introduce at least 4 variables, and we'll be using KVL and KCL. So it will be a little tedious and cumbersome for us to do that. An easier way to do would be if we are able to find out the RAB, which is the equivalent resistance across the points A and B. And in finding out the RAB, some of the symmetry rules will help us. So you can see that the horizontal symmetry, which is the symmetry about an axis which is passing through AB, is not there. It is not like clearly visible. So but the perpendicular bisector of AB will pass through this point, and there is a clear vertical symmetry which is visible. So we will just recall the 2 rules which we discussed with respect to the vertical symmetry. One was that all the junctions at which the vertical symmetry is cutting, they are at the same potential, and the second rule was that all the object image pairs of the resistances carry equal current. Not necessarily the direction, but the magnitude of the current is same. So let us name all the junctions first. So A, B, C, D, E. So you can see that the vertical axis of symmetry is not cutting except E at any other junction. So the first property of the vertical symmetry is not useful to us. For the second symmetry to be useful, we need to name all the currents which are there in the circuit, and then we can apply the same rule. So let us do that. So let's say X plus Y is the current which is going in. So this is X, this is Y, and let us assume this as Z, or let us assume this as Z and this is X minus Z. So I am just naming. So whenever I encounter junction, I name the branches which are past the junction by any other variable, and I find out the current in the second of those branches using the junction law at C. So that's why I assumed Z, and from the junction law I can find out it's X minus Z. So this is again same X minus Z, and Z is coming, and so this is Y, this is Z, and so what I can assume from the vertical symmetry rule is that 5 and 5 are the object image pairs, so as 3 ohms and so as 4 ohms. So because of being object image pair, Y is the current flowing through this 5, so Y is also the current flowing through this Y. The direction, because overall the direction of all the current is from left to right, so I am assuming the same direction. Similarly, Z is flowing through 3 ohms, and this 3 ohms will also have Z. So now we can apply junction law at X minus Z and Z. So this will come out to be X, which has to be there because of the symmetry rule, that 4 and this 4 should have the same current flowing through it. And now X will come, and X plus Y. So overall it is satisfying all the KCL rules at all of the junctions. Now once we have found out all the currents in all the branches, just recall that one more rule which we discussed was about junction isolation. So the junction isolation rule said that at a particular junction if we are able to find a pair of branches in which the incoming current is equal to the outgoing current in specifically only in that pair, then we can remove that pair of branches from the rest of the junction. And we can easily find out such two pairs at junction E, that in this branch Z is coming and in this branch Z is going. Similarly, in branch AE, Y is coming, and in branch EB, Y is going. So I can detach these two pairs from each other at junction E. So overall, if I am detaching it, so overall my new junction, my new circuit would be like something like this. So overall, now everything is detached, and the new circuit is this. So as you can see, now it seems very easy that okay, 3 and 3 are in series, so it becomes 6, and then this 6 is in parallel with this 6. So overall, this will give me 3 ohms. So now I have CD, the so now this is a simplified version of the circuit. So 3 plus 3, 4 plus 4 plus 3 is now 11. So I can just remove everything and have one resistor which is 11, and this is in series, so this is now 10 and 10 and 11. So the RAB is 110 by 21. And because I have found RAB, I can now use the value of E to find out the net current X plus Y which is going into the circuit, and after that I can find out each and every parameter of the circuit. So you can see that how can we use the second law of the vertical symmetry, and it can be really helpful to use the junction isolation rule along with it, so that we can simplify the circuit and we can find out the equivalent resistance of AB. One more thing which I need to discuss is that whenever we are asked to find RAB, it's not necessary that we would be finding it through the series and parallel combination. So one such example is this. So as you can see that it is not a Wheatstone bridge, because 2 by 1 is not equal to 1 by 2, or 2 into 2 is 4 and it is not equal to 1 into 1, 1. So it is not a Wheatstone bridge, and now we are asked, so let's say we have E, we are asked to find out what is RAB. And we cannot apply any symmetry rule or any other rule in this case, as it's visible that AB, there is no horizontal symmetry, there is no vertical symmetry. So how do we approach it? So although it seemed that okay, I should be applying some kind of trick or anything to solve this problem, but I don't think so. The easiest way, because it has only 3 non-overlapping loops, the easiest way to do that would be just to assume a current I and then break it into I minus I1, I1, and just assume all the parameters, apply KCL and KVL, apply KCL, KVL to find I, and then use this that E should be equal to RAB into I, and using this you can find I from this. E is known to you, so you can find RAB. So although it seems a little cheeky, but that's the way to do it, because there's no symmetry, there's no other thing which is applicable. So keep your mind open to such possibilities as well, that even if the question is asking you RAB, it does not necessarily mean that you have to apply any trick or do something, because in this question as well, we could have found the RAB using the same methodology, but it would be really difficult because of the 4 or 5 non-overlapping loops in that circuit. In this one, we could see that only 3 are there, and we can easily find out, and we can assume only a small number of parameters and get done with the problem. So it's your choice, and like it's a decision which you have to make after seeing the question, and the wisdom to make that decision will come only after you will experience more and more questions. One new concept, not necessarily new, but it's based on the symmetry by axis. So the rules which we discussed for the symmetry by axis problems, we will be just extrapolating them to new concept of symmetry by planes. So what do we mean by symmetry by planes? So this question would make more sense to understand this concept. That I have a cube and every branch has a resistance. So every branch has a resistance R. So all branches have R. And now I have been given that this diagonal thing is AB, and I need to find RAB. So how do we go about it? We can see that okay, there's like it's so evident that it's a cube, it has all kind of symmetry. So how can we just proceed through it? So first of all, let us name all the junctions. So M, N, P, Q, R. So let's call it as S and R. And now let us do one thing. Let's try to find out any plane which is either passing through AB or it is perpendicular to the plane passing through the AB, so that it shows us some kind of symmetry. So let's assume if I am seeing one plane which is passing through, so see a plane ABMN. So this is a diagonal plane which is passing through AB, and it is cutting the whole cube into two identical halves by the diagonal. So it's a plane of symmetry. So similarly, because it's passing through AB, it's the horizontal. It's like horizontal plane of symmetry. So we'll use the same property that the object image mirror images, object image pair of mirror images, and the junction which are forming those pairs should be at the same potential. So because ABMN includes that plane, PQ is one pair and SR is one pair. So it says that VP equal to VQ and VS equal to VR. So what we can do is that we can just join them. PQ, SR, M, B, N and A. And instead of mentioning the resistance sign, I am just like drawing them by wires, or like these are all are resistances. So as you can see that like although the circuit is simplified, it's still not directly solvable, because this R and this R by 2, because two are in parallel. This is one thing. This can be made one thing, but still it will give rise to this. So overall, we are like at a deadlock, because now we cannot easily solve it by series of parallel combination. So it's the same situation which we found ourselves in when we were doing the horizontal symmetry, and that's what we are applying, that because it's quite similar to the horizontal symmetry, because we are finding a plane which is perpendicular. Sorry, we are finding a plane of symmetry which is passing through AB. Now let us consider another plane, and this time we will be trying to find a plane of symmetry which is perpendicular to AB. So this time we are considering a plane of PQRS. So as you can see that now PQRS is a plane which is perpendicular to AB, and it is cutting the cube in form of the second diagonal and in two identical halves. And now recall the properties of the symmetry along the plane or other axis which is perpendicular to AB is that the points at which the plane or the axis is cutting the circuit, all those points are at equal potential. So this means Vp is equal to Vq is equal to Vr is equal to Vs. Because Vp is equal to Vs, it means that the resistance which is connecting P and S does not play any role because there is no current which can flow between the 2 points. Similarly, the same thing between Q and R as well, because these two are at same thing. So what I can do is that I can just club PQRS together and I can write them as one point, PQRS. And now I can just easily simplify the rest of the circuit. So I have N, I have A, I have B, and I have M. So from N to P and Q and RS I have two resistances. From N to A I have one. From A to S and R I have two. Between A and B I do not have any. From B to M I have one. From B to PQRS or SR I have two. From M to PQ I have two. So now it's like these two are in parallel, which is in series with this one. So it's 3R by 2. It's PQRS. 3R by R by 2 plus R, again 3R by 2. This is A. And this is R by 2. And this is R by 2. So it's easy to find out the equivalent resistance between AB because 3R by 2 and R by 2 are in parallel, and so as this 3R by 2 and R by 2. So overall this will give me an equivalent resistance of R. So as you can see that in symmetry by planes as well, we can find out two symmetries. One by a symmetry of a plane which is passing through AB, and other by symmetry by a plane which is passing perpendicular to the AB. And the rules which are related to each other are quite similar to what the rules we had in the axis symmetry. And we have shown that in this case as well, the symmetry by the perpendicular plane is better because it gives us one more relation than what we generally get in the symmetry by the plane which is passing through AB. One modification can be done in the question in which I can have that, okay, instead of this being B, this can be R, and I can modify this to be B. So in this question it is very difficult to find a planar symmetry which is perpendicular to AB, because like what planar symmetry will you find, because all the planes will be parallel to AB. So what you can do is that you can use the symmetry by symmetry plane which is passing through AB. So let us consider in this case the plane AB MP. AB MP. So the plane is passing through AB, and we know that the object image pairs of reflection of the junction are at same potential. So that means Q and R at same potential, and N and S are at same potential. So we can just join them and we can just make this like this. So overall we can simplify it by saying that N and S are at same potential, and so as Q and R, and we have P, M, A, B. So now I'll just be mentioning the resistances through wires. So we have P and M. Q and R are equal, so I have two resistances here. Similarly between P and NS. Between N and Q, because N and Q are so like, okay, so N and Q, and one is between S and R, and between A and B I have 1, and between A and S I have 1, and A and N, and similarly this. So you can see that it's quite easy to find out the equivalent resistance now between A and B, because this is R by 2, R by 2. So this will be R, this will be R. This R and this R by 2 are in parallel. So overall I can remove this, and now this has become R parallel with R by 2. And now these three are in series. So overall I can find out the equivalent resistance across AB in this configuration as well. So let's find out what is the value of this. So R by 2 in parallel with R gives me, so 1 by R plus 2 by R, so it gives me R by 3. So R by 2 plus R by 2 plus R by 3 is 4R by 3, and now this 4R by 3 is in parallel with R. So this is in parallel with R. So 3 by 4R plus 1 by R. So overall the net equivalent resistance across AB in this case comes out to be 4R by 7. So now you can see that, okay, the symmetry rules are so useful, because otherwise in this question it will be really difficult to apply any other formula and find out the answers. Although these questions are rare, but you never know that one such question can come and it can ask you to apply any of the symmetry rules. Although the symmetry rules are not very explicit, but they are implicitly observed and find out. What we have done is that we have laid down the rules so that you can directly remember them and use them whenever you feel like. And there is nothing wrong in using any symmetry rule or any junction isolation rule, because it's only the observations which have been gathered after doing multiple questions and experiencing different scenarios of different questions. I hope that overall the chapter of DC circuits, along with all the concepts which we have introduced, along with all the problem solving skills which we have introduced, and in the end with some of the questions, you are able to gain insight of all the concepts and some tricks which we have tried to show you with some questions. For any questions, please contact us, and we'll try to incorporate whatever you feel like. And do check out the other videos of this chapter as well, so that it will be a complete set, and you can just bridge the gap between what has been done in one of the videos and in the other videos. Thank you.